One thing that we might ask ourselves is, why do we use differential circuits in our voltage amplifiers? So let's look at, say we have an amplifier, and this amplifier has a voltage gain of AV, and it's got a wire coming into the amplifier and a wire coming out of the amplifier. Now, let's say that we also, right next to this amplifier, have another wire that's on an integrated circuit, for instance, and these wires would be coupled together. They're metal separated by insulators, so they'd be coupled together by some parasitic capacitance. So we often use the term parasitic for undesired components. So this would be a parasitic capacitance. Now, let's say that we have that this wire has a lot of noise on it. Maybe there's some digital switching going on, or just some general noise disturbance on the wire. And noise is some random process that isn't periodic at all. And it's got a zero mean value, but the bottom line is we don't know what the value of noise is at any given time. It's just random with a zero mean. And now let's also say that at the input of this amplifier, we have a small sinusoidal signal. You'll have to pretend that I can draw a sinusoid, but let's say that this is a small sinusoidal signal. Now, this noise is going to couple directly through this capacitor to the input line to this amplifier. And it might be attenuated somewhat, but just pretend that this is noise coupling directly over, and if the capacitance is large enough, then the noise is going to couple quite efficiently to the input line. Now this amplifier has a gain of AV, and it's ideally got a gain from DC to daylight of AV, which is quite large. Now we at the output want to see our input signal boosted up by whatever the gain factor is. So let's say that our output, we get this sine wave that we wanted to get. But look, our noise signal has almost the same amplitude as our input signal. So you might imagine that our noise signal is going to be amplified, and at the output we're going to see both our sinusoid and noise. And the noise is going to serve to try to hide or cause a degradation in our ability to detect this output signal. Now, let's assume that we instead look at a differential circuit. So here we're going to look at our operational amplifier that has some differential input and a single-ended output. And we're going to have the same scenario. We have a supply line or some kind of line that has a lot of noise on it. We have wires. So now we're talking about real-world problems. We have wires. And each of these wires has a capacitance that couples from this noisy supply line to the input line. Now this noise directly couples across the lines again. There might be some attenuation, but again, the idea is that the noise is coming in at similar amplitude levels. But the thing about the noise here is that this noise is what we would call common mode noise. In other words, the same noise couples to both sides of this input line, so it would add in phase together at the input. Now, on each of these input lines, we're going to put a sinusoidal waveform that might be quite small. But remember, these are differential sinusoidal waveforms, so they're 180 degrees out of phase. At the output, we're amplifying the difference between these this input on the non-inverting terminal and the inverting terminal, and we would hopefully get something quite large. We're also taking the difference of the noise, and remember the noise is coupled in phase to each of these ports. So the noise ideally would cancel out. If it doesn't ideally cancel out, it would be very small still, because we're taking the difference between it. Now, we also might have some coupling from the output line to our noisy trace up here. But remember, this coupling is just kind of direct, so the amplitude doesn't change very much. So when we use this differential mode signal, we get a differential mode output. Our input referred noise is suppressed. It's a common mode noise. And even though our output noise isn't suppressed, it doesn't have the gain from the amplifier. So it's small. So anytime that you see a differential amplifier and you wonder why would you use a differential amplifier rather than a single-ended amplifier like the first example, it's simply because it helps us to suppress noise and amplify our desired signal and be able to detect our desired signal in the presence of noise. So we'll stop there for this lesson, and in the next lesson we'll start looking at matching. One of the things that we're going to find about these differential amplifiers is that we get these differential amplifiers using symmetry, and so matching between transistors becomes very important because we need good symmetry in order to get this desired differential mode output and cancel our common mode input.